So last time we discussed, well, let me review actually here because there's apparently been updates here to what realizes or what is described by a continuous variable system. I learned yesterday or this week that there's a fifth setting, free electron light interactions. And I guess I wanted to also sort of rehash here that there's quite a few technologies, some of which have really a fine level of control, these oscillators, up to say 15, 20 Fock states for the microwave cavities. Also that GKP states, so these famous lattice states that everybody now I guess knows by now, have been realized in the first two platforms already. And by realized, I don't mean just initialized in a state and then just decays. I mean like active error correction to some degree of some sort of derivative of the original plans for this error correction has been realized in both of these technologies. I discussed it a little bit briefly last time where I was telling you that instead of measuring an analog continuous syndrome, they would just measure the sign of the displacement of where the error took the lattice, and that was enough, and it was a bit surprising that should be enough. So we discussed last lecture the left set of codes, which were stabilizer codes. They sort of had a translation-like flavor. They were lattices, and they were also hyperplanes in the phase space. Analog stabilizer codes, I didn't tell you this last time, but they're sort of picking a basis for a hyperplane in this multidimensional phase space and storing a single mode or many modes, k modes, in the n mode space. So k-dimensional hyperplane and in 2k-dimensional hyperspace and 2n-dimensional phase space. GKP codes pick a 2n-dimensional lattice in the 2n-dimensional phase space. And that stores a discrete amount of information, a qubit. And they're both described by groups of displacement operators, stabilizer groups of displacement operators, right? The group was continuous in the case of hyperplanes and discrete in the case of GKP codes. So today we're going to deviate from that, and we're going to do the second panel, which are more sort of rotational flavor codes that are not described by displacements, and most of which are not described by stabilizers in the conventional sense at all. And so I will try to introduce them in a gentle fashion by starting with something that is described by stabilizers and then slowly removing all of the nice features, some of the nice features of stabilizers to get at these codes. Any questions to that? So the code I'll start that does have bona fide stabilizers is the rotor GKP code. Apparently, this free electron is also a rotor. It forms this ladder of infinite angular momentum states. So a planar rotor is described by, the positions of a planar rotor are described by a particle, the configuration space of a particle in a ring, which means the angular position is just an angle, let's say phi, and the angular momentum is described by an integer, and it's a doubly infinite ladder. And so in contrast to the oscillator, where the position was non-compact and infinite, and the momentum was non-compact and infinite, here the position is compact and infinite, and the momentum is discrete and infinite. Okay? And you could imagine, hopefully, I mean, it's not too difficult to imagine that you can also put combs on such a position space of the rotor. So here in part A, I'm writing down position states x of this rotor GKP code, and the black balls form a linear superposition for the logical 0 state. The white balls form uniform linear superposition for the logical 1 state. And you can put n black balls, n white balls, and you will have combs that interleave like this on a circle. So here, and for the rest of this talk, I'll just be dealing with the n equals 3 case. Mercedes-Benz, 3 black balls, 3 white balls, right? And In part B here, I'm just reminding you of the linear GKP case, which is also consisting of interleaving combs of black and white balls, but now it's on the line of the oscillator, while in part C, it's on the ring of the rotor. So you can imagine that this rotor GKP code inside this rotor space will protect against some amount of rotations. The rotations that take you out of the code space will be detectable, right? And that's the yellow region in both of these cases. And rotations that don't take you outside of this, Voronoi cell, so this arc defined by the green region, are correctable because they go all the way up to the midpoint on the circle between the black and white balls. Okay? But we're dealing with bosonic codes, right? And rotor states here on the left, phi and L, are related by this discrete Fourier series situation. And we want to take this intuition behind this rotor GKP code and put it inside the harmonic oscillator. Okay? So rotor states here, importantly, utilize integer angular momentum. And our harmonic oscillator doesn't really have a doubly infinite ladder like that. It has only a singly infinite ladder, right? The Fock states. So it's bounded from below. So it's not going to be quite a 100% kosher rotor analogy. Nevertheless, it will take us pretty far in trying to define codes, such as the CAT codes, that are defined for the oscillator. So we're going to treat our harmonic oscillator now not as some phase space, not as consisting of some phase space that you could put lattices and hyperplanes on. We're going to treat it now as a fake rotor. The angular momentum degree of our fake rotor will be the Fock state. So the Fock state number n will sort of act like as an angular momentum. Again, there are no negative momentum states. However, if you are in a high enough Fock state that you don't see that you have a floor at 0, you're actually going to feel like a rotor pretty comfortably because you don't know that there's no negative Fock states, right? This type of approximation is done in condensed matter and in other physics areas all the time. However, if you're close to 0, you're going to feel the floor, and it's going to be different. Okay? The angular position degree of this fake rotor is going to be these states, which are equal linear superpositions of the Fock states, defined in order to mimic equal linear superpositions of the momentum states with some phase, and they mimic the angular position states of this fake rotor. They are called the phase states. Who's heard of them? Okay. So they...
What's the length of phi?
Angle.
But it's what? It's or any angle is fine?
Any angle is fine. Because you can, yeah, it's unique for any of those phi. And one of the first problems you'll see is that these states are not quite orthogonal. So this is a periodic delta function. This is what you would expect them to be, just like position states of the oscillator, to be direct delta orthonormal. But there are other terms that don't quite make these orthogonal. Some tangent of phi minus phi prime, I times tangent. It's again because there's no negative Fock states. So
what's the relation between
direct delta. Direct delta function, periodic direct delta function, yeah. Yeah, these form, there's a regular representation of the U1 group here, so everything is fine. Sorry, here. So, okay. So let me just throw out these equations because they're not really widespread in the literature. So one of the reasons I want to think the oscillator is a fake rotor is because there's a nice, more or less nice error basis for this. So remember, we had the Paulis for qubits, we had displacement operators for oscillators. Both of those sets form bases for all operators on the code space, and so you can expand any error operator in terms of those, and you can see whether it's supported mostly uncorrectable or mostly uncorrectable displacements. So these fake rotor situation also has these types of operators that have similar properties. So let's see. Right. So there's two sets of these types of operators. One is sort of related to momentum kicks, changing the momentum, and the other one is related to changing the position, of course. The momentum kicks are described by this things I call phasers. Well, these are called phasers in earlier papers. These are the lowering operator, but without the square roots, with the square roots removed, because the square roots are kind of obnoxious here. This mimics the momentum kick operator B, actually, that you all saw yesterday in Iro's talk. Okay? This is not quite B. It doesn't have the same commutation relations as B because there's no negative Fock states. But it does basically the same thing. It just shifts you around. Okay? And there's an integer number of them. And rotations in, so things that rotate the phase states are things that are diagonal in the momentum basis. Well, that's just Fock space rotations. They're generated by this number operator and hat, which is diagonal in the Fock state basis. So momentum kicks and position shifts. And these, this thing is not quite B, nevertheless. If you're far away from the origin, again, it kind of looks like B. And these things, for all values of the Fock states, actually form the right number phase commutator that you would expect for a normal rotor. If you commute them, you get a phase, I phi L. And, yeah? It's not unitary. You are not mistaken. Yes, L, so that's one of the other issues, that it's not unitary, but it's almost unitary. It's half unitary. It's an isometry. So it's like Hilbert's hotel type of deal here. So for L greater than or equal or greater than 0, it shifts you over in Fock states, right? So it kind of removes the vacuum component. It shifts it up. It's like an excitation. And if you do E dagger E and E dagger, one of them is not identity. One of them is identity minus the vacuum, or minus all the Fock states up to L. So that's the bad news. The good news is the number phase commutator, which is the sort of canonical relation between position and momentum degrees of freedom, is the correct one, is the same one as it is for the rotor. And second of all, you almost get a complete orthogonal matrix basis. The orthogonality is lost, however, because the phase states are not orthogonal. So this is just, this is something you have to check if you want to check if it's a basis for all operators on a Hilbert space. You have to check that it resolves the superoperator identity on the Hilbert space, which is the first equation. And then you want to check whether they're Hilbert-Schmidt orthogonal, orthonormal, and that's the second equation. But the second equation reduces to, they're orthogonal in the L index, but they're not quite orthogonal in the phi index because the phase states are not orthogonal, so you don't quite get the delta function. So they're not as nice of a basis as the displacements. Nevertheless, they are something you can expand an operator in terms of. And so now we're ready to do this fake rotor version of these rotor GKP codes, which are called number phase codes. They were done in a paper by Combs, Beragiola, and Grimsmo. So these codes are oscillator analogs of the rotor GKP codes. And you can guess probably what the equation is. Instead of superimposing rotor position states in a circle, you superimpose phase states. These are these phase states on a circle. And here again is the n equals 3 case. And you can look at these states in two different ways. You can look at them in terms of the position states, the phase states, or you can look at them in terms of the momentum states, which are the Fock states. And each one of these representations allows you to sort of see what roughly is correctable and detectable. If you look at them in the terms of the position states, you see that position shifts, which are going to be these rotations, with theta roughly up to, what, pi over 6 or pi over 3? I never get it right. Pi over 6? Are roughly correctable. I say roughly because phase states are not orthogonal, so we have to be careful to really make clear statements. We could have made this in a real rotor, but we can't make it here. So I say roughly, so you have to sort of be more careful about actually claiming that. And then, but here the situation is cleaner. So here, these operators, these phasors that shift the momentum or Fock state number up and down by 1 are correctable because of the spacing here of these ladders in the Fock space, okay, or in the momentum space. So these are the similar types of ladders you saw yesterday in Ido's talk. They were making ladders where there was no spacing, so n equals 1. But if you blow up the combs in a way that there's some spacing between them, then you have some correctability against momentum errors. So let's see. And one of the other advantages of introducing these codes this way and going through all this phasor business is that there is actually a set of almost normal stabilizers for these things. And it's not quite the same because E is not unitary. That's the only issue. So remember, GKP states had these displacement stabilizers, and you can combine rotations and phasors to give you a sort of a stabilizer group. It's not a group, sorry, a stabilizer set. So here, remember, with qubits, we had indices in Z2. With hyperplanes, we had indices in R. With GKP, we had indices in Z. Now we have an index in Z. With the real rotor codes, we would have a Zn, discrete rotations by 2 pi over n, that leave our little Mercedes-Benz invariant, and we would have kicks in the momentum that go all the way up and down. So this would have been Z for the real rotor, but here it's just the non-negative integers because this thing is not quite unitary. So this is one of a stabilizer set that you can think of for these codes. So E dagger kicks you down by the same spacing such that the code states are invariant, and this rotation by n hat by 2 pi over n rotates the states around. Now, what's interesting about E dagger is that phase states are actually eigenstates of E dagger. With eigenvalue e to the I phi. So E dagger is like the lowering operator. Sorry about the dagger, it's a convention. E dagger is similar to the lowering operator in that it has a set of right eigenstates but not a set of left eigenstates. Again, it's not unitary, it's not diagonalizable. This thing also has a set of right eigenstates, which are the phase states, and no set of left eigenstates. So that's why we can't sort of reverse it, and there's not a group structure. However, there's this set type of structure where it is indeed true that the joint plus 1 right eigenspace of these operators forms the code space. Okay, this is as close to a stabilizer group as I could get it. So this is the best you're going to hope for today. Yeah. Sure. I don't know if you should, but you could. Let's see. So we're just superimposing phase states here, n of them. And there's a sum over Fock states here, and I've already flipped the sums. So this is, which if you're ever stuck in quantum mechanics, you just write everything out and exchange any sums that you see, and then try to add up the sum inside. So I have, remember the phase states are equal superpositions of Fock states with a phase, so I wrote that sum in right there in that step. And then I switch sums, and I'm going to evaluate this inner one. And this inner one is just this sort of discrete Fourier transform it means that the Fock state has to be equal to 0 up to z mod n, or Fock state n is 0 modulo z sub capital N. Okay, so that's how equal superpositions of Fock states give you spaced out. Equal superposition of phase states give you spaced out. A similar situation occurs if I had shown you the GKP codes. Oh, this is just the non-negative integers. It's just the natural numbers plus 0. Because I still remember my set theory from undergrad. They obsess about this, right? And again, it's because this thing has right eigenstates but not left eigenstates, and the one with L less than 0 has left eigenstates but not right eigenstates. So I'm not including that one because I want to fix a set of operators whose joint right eigenspace forms the code space. So I'm excluding the negative L situation. If I was not, if I had a real rotor, I would not have excluded them, and I would have had a bona fide stabilizer group here. Okay. You can. Yes, some people write it like this. So this is indeed a position, or is a momentum kick type operator. So if we had a rotor, we would write phi hat, e to the I phi hat times something, but we don't have a phi hat. The oscillator phase operator is something that has a long history and people have actually made mistakes on. So I don't write it this way. So, but people in oscillator world sometimes write it as a big hat over the whole thing. I just fixed it as E. Well, there is no phi hat per se for the oscillator, so. And also this sort of makes it look like it's unitary because it's got an E to the I in it. Anyway, it's just a convention. But yes, this is an alternative way of writing it. Who knows the history behind the phase operator? Who was it? Who screwed it up? Dirac? Somebody famous screwed up, tried to define this thing, forgot that it's a Hilbert Hotel situation, and I think thought it was, what, unitary or something? But I think it was Dirac. And then Susskind, Lenny, and someone else fixed it. And then Peg Barnett and all these quantum optics people developed it further, yeah. Who? Glow Gallower? How do you? Yeah. I don't know how to say their name, but it's okay. So this thing's what used to be a bit finicky, but honestly, just besides the fact that there's no negative Fock states, there's really nothing to be worried about it, and the fact that it's not unitary. Okay, so we have our nice sort of polar picture of the harmonic oscillator of a single mode. Let's introduce the cat codes by going doing as follows. So if you draw a phase state in the phase space of the oscillator at angle phi, the only parameter here is phi. What does it look like? It's a ray. It's a ray at phi that goes off to infinity. It's an infinite superposition of Fock states, so it's not a normalizable state. Remember, the phi and phi prime blows up if phi equals phi prime. And so it's basically kind of like that. We want to do normalizable versions of these states, right? So let's sort of tone this down and make it a blob at phi, a Gaussian blob. Now the Gaussian blob picks up another parameter. Where do we place it in the radial direction? We can place it anywhere we want. Let's call that parameter alpha. And now, instead of writing rays, we write blobs at some alpha, and those are nothing but coherent states. So instead of superimposing phase states, we superimpose coherent states, and we get the cat codes. Okay, so this is one way to understand the cat codes. We just have a normalized or regularized version of the number phase code. What does that mean? It means that this modification has inherited some of the features of the number phase code. So first of all, these coherent states are spaced some angular distance apart. So as long as the radius is not too small, in which case you wouldn't be able to resolve them, as long as the radius is sufficiently large, you're going to have the protections against the rotations and angular dephasing that you enjoyed with the number phase codes. Similarly, if you write these cat codes like I had written, if you substitute here alpha e to the I phi coherent state, and you do this math that I just did, you get the same orthogonality relation. You inherit directly the same spacing in Fock space. So you're also protected against jumps in the Fock state number or angular momentum kicks. So these types of cat codes are very similar in their level of protection as the number phase codes. However, as was the case with the phases, with the number phase codes, coherent states are not quite orthogonal, and so we have to worry about corrections to exact correctability. Now, once we do this step, we gain normalizable states, but we lose the phase operator. We lose these phasors. What do I mean by lose? Well, they are no longer relevant to describe the stabilizer set of this code. Phase states were eigenstates of these positive L phasors. Similarly, but only right eigenstates, not left eigenstates. Similarly, coherent states are eigenstates of, again, right eigenstates of the lowering operator. Who knows the coherent states are eigenstates of the lowering operator? Okay, good, yeah. So that was hopefully a prerequisite, but yeah, so there's this lowering operator in these coherent states, which are classical sort of analogs of a normal swing, a normal classical mechanical oscillator. And they happen to be right eigenstates of the lowering operator, but the lowering operator doesn't have a set of left eigenstates. So we have to, our stabilizer-like operator now becomes this lowering operator and its powers. So instead of E sub L being 2n, shifts by 2 capital N, now we have A to the 2 capital N as our stabilizer-like operator. Okay, and because we have, but this actually brings us to something fairly physical. So the bad news is that A is even worse than E. It's not only non-unitary, non-diagonalizable, it also has this annoying square root. And so we can't even, multiply them together in a nice way, and it's not even half unitary, right? Because A dagger A and A dagger are as far away from the identity as you want. However, A is actually a really physical operator. And this brings us to a way to stabilize these cat codes to protect against this rotation noise that's not available elsewhere. You can use Lindbladians. Who knows what a Lindbladian is? Okay, good. So you can think of this Lindbladian as imposing a potential well on our phase space. So now we're back to phase space, and let's imagine we have a double well for the case capital N equals 1, or we just have one state per, we don't have 3 states per code word, we have just 1 state per code word. So the states are now alpha and minus alpha. Capital N is 1. Our stabilizer is A to the 2n, which is A squared. A squared, the eigenstates of A squared are coherent states with eigenvalue alpha squared. For plus alpha and minus alpha, it's plus or minus alpha squared, which is just alpha squared. So if we want to cook up something that annihilates these coherent states, we just subtract alpha squared. So A squared minus alpha squared annihilates both cat states plus and minus alpha. And if you put this in a Lindbladian, you can show that Lindblad evolution, which is this type of dynamical equation, admits 2 steady states, one of them at plus alpha, one of them at minus alpha. And you can sort of, again, think of it as a double well situation. If you had A to the 2n, you would think of it as a potential well, on a circle with 2n minima. Okay. And this Lindbladian has actually been realized several times by the Yale group. So, so it's really cool that it's really a bona fide open system with degenerate steady states, and it's been realized, and that was something I had started out working on in my thesis, actually, in the beginning of grad school. So this stabilization protects you from small shifts, because as soon as you kind of roll away by a rotation, the Lindblad will draw you back. This is a form of passive stabilization. Remember, we discussed in quantum error correction, you have these active, discrete, stroboscopic recovery cycles steps where you extract information, you measure some not so good quantum numbers, and you apply corrections. This is sort of a continuous version of that. It happens without you having to measure or remember anything. And this is the idea behind the CAT code's sort of protection. It's sort of the only way to really protect against these rotations. There's not really a nice discrete way of doing it. If you can figure out a discrete way of protecting against rotations that replaces this type of system, it would be very nice. Yeah. Yeah, you have to engineer. You have to engineer the environment. You remember, if you derive Lindbladians, you start with some environment, you start some system environment coupling. The coupling has to be basically this type of multi-wave mixing, A squared B dagger. And then you trace away the B mode, and then you get this A squared mode. To get the alpha squared part, you have to drive the A mode by alpha squared. So you have to squeeze the A mode while at the same time having it interact with a B mode that is very lossy. And then you trace out the B mode and you get this jump. Yeah. Good. That was exactly the question they asked me when I started grad school. What does the Lindbladian do to superpositions of initial states? Let's say I start somewhere else in the phase space, right? What happens? If I can start in a classical state. I can start in 1 alpha. I can start in a CAT state that's close, and the well will bring it down. Does it kill the coherences or not, right? What was your second question? Yeah, so good. So what it does, if you start in a classical, just a normal alpha, next to the wells, it just goes into the alpha in the well. If you start with a beta close to one of the alphas, it goes in. If you start in a superposition, it more or less maintains the coherences, especially if you start in a symmetric superposition. So if you start in something that's scaled down, it'll blow it up like this and maintain perfectly the superposition. However, if you start somewhere in between the wells, then you'll be spread into this superposition and it'll be a mixture. So you decohere if you start sort of along the line bisecting the 2 points. But if you start in a superposition where one point is near one of the wells and another one is near the other well, you actually are maintained. And that's why the error correction actually works. But if you go too far, you're kind of screwed. Okay.
Does it make any sense to consider, say, Lindbladian into the sum over alpha? Or is it
Where's the sum?
I mean, this Lindbladian is parameterized by alpha.
Yeah.
Makes sense.
Yeah.
But I could look at sum of that. Lindbladian makes sense.
Well,
This is the prototype.
for this, you don't need it. You just have this one jump. And because it is, you can understand why things are problematic at this bisecting line because of discrete error correction. If your rotations are such that you get out of your Voronoi cell, then you don't know where to go. You get misidentified and you get logical error, so you get dephasing. So the Lindbladian, because it's doing sort of a continuous error correction, it has the same issue. But if you don't leave the Voronoi cell, the Lindbladian does a very good job. So we actually, last week, we generalized these codes to codes on the higher dimensional sphere. This is a one-dimensional sphere, a complex one sphere. And you can do higher dimensional coherent state spheres. And there you do need multiple Lindbladians to stabilize the multi-well potential. I don't want to advertise it, but it is kind of a very straightforward generalization of these types of designs. Okay, one more code. You already saw this mapping. Don't overthink it. It's really just a heuristic for this binomial code. This, again, you can think of as a CAT code. Why? Because it has the same type of spacing in Fock space as the CAT and the number phase codes. We, again, have a spacing. However, now, as opposed to the CAT and the number phase codes, we have finite support. We only go up to some maximum Fock state. So this is sort of a digital version of the CAT code. And more generally, this is what binomial states look like. if you take actually plus minus, so the bottom equation should be the plus minus basis, and the top is 0, 1 basis. No, sorry, this is also 0, 1. These are the binomial codes, and more generally, they have a binomial envelope, okay, as opposed to the CAT codes having a Poisson-like envelope, and the number phase codes being flat. These have a binomial envelope, which terminates, as the binomial distribution does, and they are also spaced apart by capital N. So all three types of codes protect against kicks in the momentum or losses and gains in the photon number. And there's some protection against rotation errors as well. I want to sort of reiterate, so the photonics people often use this type of code. This is called the dual rail code, and this maybe should have been introduced in the very beginning. This is a simple but non-trivial example of a digital type Fock state code, right? It's finite support, it's in the Fock states, it's intended against photon loss. What does this code do? So hopefully we're now learned enough about error correction to you can tell me what this code does. Does it correct anything? Yes, it's plus. There's also a typo. Good. That was there on purpose. What does it correct? Does it correct anything? No. Does it detect anything? What does it detect? What? It detects a single loss. So if you lose a photon in this 1, 0, and 0, 1 space, if you lose a photon in the A mode, 1, 0 goes to 0, 0, 0, 1 disappears, goes to the 0 vector, and you have a click on your photodetector. If you have a loss in photon in mode B, 0, 1 goes to 0, 0, and 1, 0 disappears, and you get a click on your photodetector. So when you get a click, you know that this qubit destroyed itself, and you start over. And so when you see the photonics people like PsiQuantum talk about something called success probability, that's the probability that they post-select on. They post-select on events where they didn't see the click. Okay? And each of their physical qubits is in this dual rail setup, and they have to not have a click on all of them, and they post-select on such events. And the success probability is the probability that such events happen. So they are using a basic form of error correction, okay? And it's the dual rail code. Right, so how do you measure these things? So this is a review. Last time we talked about these type of lattice and hyperplane codes. GKP codes would, the syndrome there was the position, the modular position, the position modulo the spacing of the comb, and the momentum modulo the spacing of the comb. Similar here for these number phase codes, which are the closest analog to rotor-based GKP. You have to measure the spacing of the comb you have to measure the angular orientation modulo the spacing of the comb, which is called the modular phase. There's a way to measure this using these phase states. And then you have to measure the Fock state spacing, the spacing of the comb in the Fock space, the Fock state number modulo the spacing of the Fock state comb, which is called the modular number operator. And so you basically, what you're doing for the number phase codes, as I should have mentioned this before, is that this stabilizer group that I write down here, S number phase, the two operators that generated are precisely the two things whose eigenvalues you're going to measure. Now, I told you that E daggers are not quite diagonalizable. Nevertheless, you can measure their eigenvalues using phase measurements. So this is the beauty of these phase states and other states that are not normalizable. Even though they're not normalizable, you can still use them to resolve the identity, which means you can use them as a measurement. You can measure their parameter. So the number phase codes are as close as an angular analog to the GKP codes, which are linear. The CAT codes inherit some of that. So remember, they still have the same spacing in Fock space. So do the binomial codes. So the modular number operator still tells you where you are in the Fock state ladder. And then these dual rails, as you saw, you only just measure number and detect a single loss. I didn't go into any of these other more digital codes, but there's plenty of them, so if you want, you can explore the error correction zoo. How do you measure, some of you asked, how do you measure these modular things, right? They're complicated. Well, one of them is not. The modular number operator, which is the Fock state number modulo capital N, can be done in circuit QED setups very easily. And the reason is because they have a conditional type of rotation here. Yesterday, you discussed a conditional displacement, right? It's an interaction between a qubit and an oscillator where the oscillator is displaced conditional on the state of the qubit. Here, we have a conditional rotation. The oscillator is rotated conditional on the state of the qubit. The interaction here is this D, A dagger A, and E is the excited state of the qubit. And there should be A dagger A, E cat E bra here next to the capital D. So this thing, if you write it out, if you evolve to pi over chi, the chi's cancel, and you write this thing out, it becomes basically a C0 type of gate. It applies a parity operation or a rotation by 180 degrees, conditional on the state of the qubit being an E. And when you sandwich this by qubit Hadamard's, you get a projection. You get that you split up the positive and negative parity subspaces of the oscillator into the ground and you entangle them with the ground and excited state of the qubit. And this allows you to do a parity measurement. So in circuit quantum electrodynamics, this is something that they have done since 2014. This is super fast measurement. This is so fast that they had to slow it down in their experiment because it would have caused less noise for them to do it a little slower. And so this is sort of a standard workhorse that they have that allows them to realize a lot of these cat code schemes. So I just wanted to mention that because I thought maybe some of you, well, we're starved of experiment here, and I think it might be nice to have a slide or two, as much as I like theory. So that's basically wrapping up. I wanted to, how much time do I have? So I wanted to mention a little bit briefly about physical noise. Remember, I just discussed sort of shifts in phase space, rotations, momentum shifts, but what is actually going on in the lab in terms of noise? Well, here it is. There's 3 dominant noise channels for these technologies. I don't know what the noise channel for the free electron is. You guys tell me. But for the other ones, there's something called attenuation or photon loss. And this is just something that's very related to losing angular momentum in the downward direction because you have this loss operator here. So this is sort of a contraction in phase space that brings you down to vacuum. Then you have dephasing the trapped ions have these frequency fluctuations. So it's dephasing because it's generated by the number operator. It's sort of, you can sort of think of this as a bunch of random rotations happening, which wind up smearing you around in the angular direction. And then the third noise is actually, it's called additive Gaussian white noise. It's actually literally displacement noise. So the noise we had looked at with respect to GKP codes is actually really just a normal physical noise. And right, so loss is a contraction, dephasing is radial diffusion, displacement is linear diffusion. But it turns out that if you do loss, and then you do the opposite of loss, which is phase-insensitive amplification, which is also a noisy process, you get back to where you were in energy. You kind of breathe out and breathe back in, but you have diffused. So loss followed by amplification gives you displacements, gives you a little bit of diffusion. And this is something that allows you to answer the following question. Which code does better against the dominant source of noise? In this case, we're going to do loss. We take our codes, we figure out the best possible recovery we have given the noise rate and the noise channel, which in this case is loss, and we optimize over all codes, and we plot the rate of recovery. Here in this case, it's a lower bound on the communication, but it doesn't matter. This is the loss channel. So this is something that codes that have a Fock state spacing are designed to protect against. So which codes are those? Cat and binomial. GKP is not designed to protect against this. They're designed to protect against shifts, diffusion in phase space. However, GKP is doing pretty good. So what's going on? This was a very surprising result that we found. And back in 2017. And one of the ways to explain it is that even though GKP is not designed to protect against loss, if you take the loss channel and then you follow it with a recovery that just does a phase-insensitive amplification, you obtain displacement noise. Oh, looks like my time's up. You obtain displacement noise, which is exactly the noise GKP codes are designed to correct against. So you can convert noise into other noise using noise. That should be clear. I mean, so what happens in over there? Oh, there's just some artifacts of the optimization. I was optimizing over all codes, and the single rail code is just the 0-1 Fox state code, and the CAD and binomial codes have that as one of their codes, and the GKP codes do not. Okay, so that's it. If you go to my review, I have a whole list of sort of the uses of an infinite dimensional Hilbert space in terms of no-go theorems. I don't want to, I mean, I can discuss this offline. There's lots of no-go theorems that in finite dimensions, but they can be circumvented in infinite dimensions. So I'll leave you on a positive note that, you know, CV systems are not something that will solve all our problems, but in principle, I think using an extra CV layer of correction, if we have the technology to do that, will help us in our quantum tech. So thank you for that. Thank you for your attention.
So, thanks for the talk. There's time for a few questions, as mentioned before. I noticed a lot of talking nonsense, but now when you're using your code, you're using your inference stabilizer. Due to energy conservation, all the operations that you experimentally run your computer are unified. Meaning that you couple your qubits to the environment, maybe not strong, but you still couple. So experimentally using this kind of code add more noise to your system, or there are no evidence for this?
Because of the non-unitarity? It sometimes can do that, actually. The schemes in the GKP code that the experimentalists are doing, they don't necessarily add more noise, but they can add more energy. They kind of go all over the place in energy. But so a unitary process can do that. I guess the short answer is really not it's okay. So, well, if you leave the well and your Lindblad takes you back, yes, that's an irreversible process, but it's okay because it's a stabilization process that has maintained the superposition within the code space. So it's okay in some sense. Yeah, so maybe I should emphasize that you already know what something called a threshold is. A threshold is basically the ability to do computation arbitrarily well. It's something that requires an infinite family of codes in a tensor product space. So it requires you to have tensor products of some subsystems, qubits, oscillators, whatever. A single mode code will not have a threshold, is the widely held belief. It's not something that's been proven, but it's something that people really believe. So all these sort of cute single mode, lattice rotational codes will not give you arbitrary high precision computation. You still need to scale up using tensor products. And what I mean by the quote here is that people have been looking at scaling up, but in a concatenated way. They first take their physical qubits, they encode them in these nice bosonic qubits, and then they scale up these new physical qubits into a, say, surface code or QLDPC code or whatnot. And this improves the threshold. So it increases the physical noise rate at which you can do arbitrarily high precision quantum computation. And that's why I mean the futuristic combined. Similar patterns are done in classical coding theory, where you have your 5G cellular communication, you have one code for one part of it, another code for another part of it. So sort of combinations of codes are useful, have been useful historically, and the hope is that we, with CV, that CV can provide some local physical qubit that still has its own layer of correction that can help you improve thresholds and, and scale up with fewer resources.